today talk more about electricity. So let's start with basic electricity demonstrations here. So demonstration number one, taking the amber rod and putting it on the telescope. Remember last class period, it's a good thing we played with it because I borrowed that from high school and he had to borrow it back. He said, I'll borrow it back. I'm like, it's yours. But bottom line is I don't have it to play with today. So it's good that we got to see it a little bit yesterday. So I'm going to rub this rubber rod on the fur, bring it up here, and if I touch it on there, see that thing is moved. Oh, okay. Me hitting it doesn't help anything. But it's moved out. And so that is something that most of us would consider interesting. Like it was sitting pretty close to straight up and down. Now it's not. There must clearly be something pushing this vane away from the fixed part. That's something curious. Remember the whole scientific process, scientific method. You start by observing something interesting. And then when you observe something interesting, you come up with an explanation of why. So at this point, you don't have much understanding of electricity. What would your explanation of why be?
Why what?
Why is this thing not straight up and down? Like if I touch it here, you see it comes back to essentially straight up and down. If I rub this fur again, I can make it move out there again. So the question is why?
Opposites repel each other?
Okay, so she said.
No. Like repels each other. Like negative repels each other.
Yeah, make that thing push away. I'm going to touch it, make it touch. I do all kinds of things. I can put a force. So if we didn't know anything about electricity, we wouldn't be able to say what Leslie's saying. She already has some knowledge. If we didn't know anything about electricity, all we could say is there's some force that is making this and this push away. And so that's pretty much all we can say as we start. Now, another thing we can do, so we saw it pushes that away. That pushes that away, right? It's kind of cool. Now we take the glass rod. Let me just one more time, just to make sure we're clear. If I take this rubber rod and I rub it up and bring it up close to this, it makes it move even farther away. Now I'm going to take this glass and rub it on my shirt. Remember I told you I don't wear silk shirts, so it's not the exact ideal here, but so I bring this up. When I bring it close, what's it doing? It's coming closer. It's doing the opposite thing. And this attracted that. Did the opposite thing. Now it's attractive. So there's something funky going on here that has both an attraction possibility and a repulsive possibility. And so that's why people like Ben Franklin decide there must be two kinds of charge that are making a force. And so based on the Greek word for amber, we have electric, so we call it electric charge. But basically what they noticed was we had these forces, let's try to understand it. So they said we must have something that's being transferred, and thus Ben Franklin said, whatever's on the amber rod, we're going to call negative, and we're transferring between the fur and the rod so that the fur is gaining something, or the fur is losing something, and the rod is gaining something. The rod was gaining whatever he called it electrons and identified it as having negative charge. So that's the beginning of electricity. And we have things that have a positive charge, things that have a negative charge, because we have two types, and they said that's an easy way to distinguish them. And notice when I touch this, apparently the charge runs off because it's no longer doing anything. So we're going to talk about electricity today, about this electric charge interactions. I know this is really disappointing. I'm going to skip over magnetism. We have to talk about electricity because we're going to go to chemistry next. And without electricity, chemistry's a little baffling. since chemistry is quite a bit about electricity. We will, I believe, have time to at least cover music because I love the music lecture, but we're going to cut out the magnetism, so I got to put all my magnets away. I left them out since I covered them. Well, I'm still covering magnets in my other class. So we can see that there's a force. We call it electric, so there's an electric force. And this is one of the fundamental forces. We only have 4 fundamental forces that we know of in physics. The first one, gravitational force. Gravitational force is a force between any 2 objects that have mass. So mass is the gravitational charge. No one says charge when they talk about mass, but it is the gravitational charge in every way, like we have electric charge. It's what the force depends on. Then we have the electric force, and the magnetic force is actually pretty much the same as electric force, called electromagnetic force. It's very different in behavior, but fundamentally from the same force. Then there's 2 forces that only occur at very, very short distances, like inside of the nucleus of an atom. And so those are the strong and weak nuclear forces. So 4 fundamental forces. One of them is gravity that we've already studied. One of them is this electromagnetic force. And pretty much everything that we observe and see that's a force has one of those 2, gravitation or electromagnetic. Because the strong and weak are only at very short distances, like inside the nucleus of an atom. And we don't see what's going on inside the nucleus of an atom at all. Now that brings up some interesting questions, like if it's only electromagnetic or gravitational, what is keeping me from going through the floor? Up to this point, what do we say the force is that's keeping me from going through the floor? The normal force. But now I'm telling you that normal force is the result of one of those 2 fundamental forces, gravitational or electromagnetic. So which one do you think the normal force is because of? Okay, how do you want it to? It turns out it's electromagnetic. It's electromagnetic. We're going to switch to chemistry in a week. The electromagnetic force is the force that holds atoms together. And so the force holding the atoms together is what's keeping me from going through. I'm pushing and trying to pull those things apart so I can go between them, but they're holding together, and that's why it resists me going through. And as we'll see in chemistry, even though the floor is virtually all empty space, and I'm virtually all empty space, I can't go through because I'd have to separate the atoms. Okay, with the electric force, we have 2 kinds of charge, positive, and protons are an example of positive charge, and negative, electrons are an example of negative charge. Something interesting and peculiar, charge comes in finite amounts, what we call quantized. You can only have a charge of -1 electron charge, -2 electron charges, -3 electron charges, or +1 electron charge, +2 electron charge, +3 electron charge. You can't get anything that's not an integer multiple of the charge of an electron. So we have units for the charge that we call coulombs. Not yet. I think it's named after Charles Augustin de Coulomb or something like that, who did a lot of study on this. And the charge of 1 electron has Q equals 1.602 times 10 to the minus 19 coulombs with a minus sign. Q, what was Q last time I spoke to you? It was the symbol for heat. Now Q is the symbol for charge. We reuse these symbols. I'm sure you're very happy about that because it just leads to frustration. Having Q could be either one. So you have to be a little nimble. Q could be charge or heat. So the charge of an electron is minus. It's a negative charge for the electron because Ben Franklin said so. It was an arbitrary decision. There's nothing special about negative versus positive. It's just they're different, and Ben decided let's call Electron's negative. 1.602 times 10 to the minus 19 coulombs. What that really tells us is this coulomb, the basic unit of charge we use, is a whole lot of electrons. You have to get about 6 times 10 to the 18th electrons to get minus 1 coulomb. Very large number. Okay, talking about the forces, now we get to the words that Leslie was saying. Fundamental rules about charge: likes, repel. So a positive charge will repel another positive charge. So when I was playing with my rubber rod and brought it up here, and it was repelling that pith ball, or styrofoam actually, it's supposed to be pith, but it was repelling it. That tells us that the charge on my rubber rod, which was negative, because that's what Ben Franklin says it'd be, is the same as the charge on the little ball, so that they're repelling. When I rubbed the glass one, it attracted. Our rule is that opposites attract. And of course, I can test that real easily. I can start with the ball completely uncharged, have it so it's just sitting there all neutral, and then I could bring something up and touch it, then bring it up again, and if it repels, that shows me that lights repel. I actually demonstrated that lights repel with this when I brought it, touched it with the rubber rod, and then charged the rubber rod again, brought it closer, and it repelled even further. But lights repel, opposites attract. So negative repels negative, positive repels positive, and positive attracts negative because opposites attract. You have a question, Leslie?
So, which one would you identify as negative? Which one would you identify as positive? Because I know that when you rubbed it against that, it was repelled. And when you rubbed it against, I don't know what it was,
okay,
then it attracted.
Arbitrarily, Ben Franklin said the stuff on this is negative, stuff on this is positive.
What is the stuff on that?
The stuff on this that's negative is electrons. It's called electrons because he did it with an amber rod, and amber in Greek is electron.
Okay, so if that's amber?
This is actually rubber because you know what? It's cheaper.
So rubber, I just want to know what that is made of. Like, why
it's rubber. It's made out of rubber.
Oh, and the other one is glass?
This is glass.
Oh, okay.
I misunderstood the question. So fundamental rule, opposites, what do? Attract. Likes, repel. Okay, that's a very important rule. And now the basic charge carriers, protons, neutrons, and electrons are what atoms are made out of. How do we know this? It's a long story. Initially, we had Democritus, I think it was, who said if I take a piece of material and I cut it in half, I have 2 smaller pieces. Do it again with one of the smaller pieces, I have 2 smaller pieces. And eventually I'll get to an indivisible piece, and we'll call that an atom. Atom meaning indivisible. So the original model was that we just had this little indivisible piece. But then Thomson, an experiment that I talked to my class about just 2 days ago, and the other one, showed that if you have a piece of metal, it has electrons in the metal. If it has electrons in the metal, then they said, well, we must have, going through the scientific process, he noticed that electrons came out of the metal, deduced there must be electrons in the metal. That's his hypothesis. But if electrons are in the metal, then he said that you must have this clump of stuff, and in that clump of stuff you have the electrons. That's called the plum pudding model for matter, saying that your matter is just a bunch of positive charge spread out with little points of negative charge. But then we had the Rutherford experiment. You may or may not have heard of any of these experiments, and right for today, you don't have to know the difference in them. The Rutherford experiment, they thought that they were going to shoot positively charged particles. Actually, the nucleus of a helium atom, 2 protons, 2 neutrons. At that point, they didn't know it was 2 protons, 2 neutrons, but they knew it was a tiny positively charged thing. And they expected it to basically go through uninhibited, just a little slowing down because of that mushy positive charge. But if it hit an electron, it just slowed down a little more. And so they would look for how much it was slowed when it hit the electrons. So they're basically shooting a bowling ball at a screen that has just a few levitating BBs. Somehow levitating. And so they expected not much, but if it hit a BB, then it slowed down a really tiny amount, hard to measure. And what they found was these alpha particles, these healing nuclei, some of them bounced straight back. So Rutherford described it like, imagine that you have a piece of tissue paper that you've spread out, and you shoot a cannonball at it. And when the cannonball hits the tissue paper, it bounces back at you. You know, that's how shocked they were. Scientific method, they observed something interesting. After observing something interesting, what's the next step in the scientific method? Create a hypothesis that has 3 properties. Number 1, it must explain why the thing you observed happened. Number 2, it must be based on scientific ideas. And number 3, it must make predictions that you can test. And so Rutherford came up with the idea that an atom is like a planetary system with a very small, dense, positive charge at the core that we call the nucleus, and then with the electrons doing circular orbits around it, like you see in that picture. Why did he come up with that model? Well, it explained why you would have the alpha particle bounce off of something. It's going to bounce off of something heavier, not off of something lighter. If it hits something lighter, they're just going to travel the same direction. It slows down a little. And he was actually able to identify what the size of that nucleus would have to be. Now, quickly, there were problems found with Rutherford's model as well, right? It makes testable predictions, and some of those predictions didn't turn out right. And so our current model is not the picture shown here. If you've taken a high school physics or chemistry class, you probably have seen this picture. And a lot of people think that's our understanding of an atom. It's not. Our understanding of the atom is that we have a nucleus at the center that has protons and neutrons. Protons, little particles with positive charge. Neutrons, little particles that have 0 charge. And then we have electrons that are whirring around about it, and we don't know what their path is. We don't know how fast they're going. We can tell you what their angular momentum is. Angular momentum is like linear momentum, except for you're going in a circle. So linear momentum is how hard it's going to be to stop you. Angular momentum is how hard it's going to be to stop you from rotating. We can measure their angular momentum. We can measure a number of things, but we don't know where they are. So when you see pictures of an atom, the reason we draw it like this is because we don't know where the electrons are. So we're saying, well, they're somewhere out here. And you might see orbitals, things that like a p orbital looks like that. That does not mean that the electron is traveling on that path. What that means is if you look for the electron, you're most likely to find it somewhere in that area or that volume. It's just telling you where you're likely to find it, because we can tell you where it's likely to be found, can't tell you where it is, can't tell you what path it's doing. Okay, so all of this to say that our matter is made up of electrons, which have a negative charge and orbiting around, protons at the center with a positive charge, and neutrons at the center that have 0 charge. If a neutron has 0 charge, what does that tell you about the force due to the electromagnetic properties? Opposites attract, likes repel. What is a 0 going to do? It's a weird idea to us because with mass, we don't have a 0, except for light. Everything we know of has mass. It all has a positive mass. With charge, we have some things with a positive charge, some with a negative charge, and some with a 0 charge. 0 charge will have no electromagnetic interaction. It simply won't be affected. Positive will be attracted by negative, repelled by positive, negative the opposite. The neutrons with their 0 charge simply don't have an electromagnetic force. It's not an option for them. They can only have gravitational force and, of course, the strong and weak. Now, recent advances, and recent advances means roughly from the time I was born on, which puts it the last 50 years, have discovered that the nucleus is not just protons and neutrons, but that protons and neutrons are made up of quarks. quark is a nonsense word from James Joyce's book, Finnegan's Wake. That poster in the back is illustrating what protons and neutrons are really like. The picture in the center is showing a helium nucleus. The helium nucleus has 2 protons and 2 neutrons. If you look up there, you can see, okay, I can see 4 things, but each one is made up of 3 smaller things. Those 3 smaller things are the quarks. And a proton is up, up, down, and a neutron is up, down, down. One has 2 ups and a down, the other one has 1 up and 2 downs. The ups and downs are the names of quarks, because scientists got all interesting like. And they said initially, hey, we have 2 kinds of quarks, let's call them up and down because they're opposites, just like plus and minus were opposites. But then they found that there was some strange behavior. So they said, must have a third particle that we're going to call the strange particle because it causes strange behavior. It also has another name, sideways, because sideways would be between up and down. No, quarks. It turns out it's a higher energy state.
No, but you said that there's another thing on top of it. Where?
Well, in the nucleus, you have protons and neutrons, but protons and neutrons are made of quarks.
Oh.
And the first 2 quarks were up and down. But then they found there's something gave strange properties, and they called it strange or sideways because it's not up and not down. And then they had a theory that said there should be 4, and they only had 3, and so they said the 4th one must lead a charmed life because we can't find it. So they called the 4th one charm. And then their theory expanded and said there had to be 2 more, and so they chose another pair of opposites, top and bottom. And then some scientists said, wait, no. We have strange and charm, and then we go to top and bottom. And so the alternate names for top and bottom are truth and beauty. So those quarks are things that protons and neutrons are made up of. We will not study the quarks at all. Just wanted to point out that this is kind of a simplistic view, but if you would go back 100 years, this would have been a very complex view. It was about 100 years ago, 115 years ago, when this planetary model of the atom was invented. And if you go back 120 years ago, it was just Democritus's idea of, you break down to small pieces, the end. So it's relatively recent that we have this understanding of atoms. Now that I am over half a century, I'm like, wow, that wasn't so long ago that we knew nothing. Physics would have been so much different if you were taking it 150 years ago. But it's good that we've advanced. So atoms are ideally electrically neutral. Electrically neutral means the net charge, the total of positive plus negative, is 0. So you have as much positive charge as negative charge in an atom. What has a positive charge in an atom? Protons. What has a negative charge? Electrons. So a neutral atom should have the same number of protons as electrons. Now, if you look at that periodic table of elements back there, you see that it has the top left corner H, and inside the box, top right corner inside the box, it says 1. That number in the top right corner of the box tells you how many protons are in the nucleus. Each box is a different element, and the elements are defined by the number of protons in the nucleus. So H has 1 proton, go over to the right, He has 2 protons. If it's neutral, how many electrons should He have? 2 protons. If it's neutral, how many electrons should it have? 2, because they have the same magnitude of charge, that's the same size of charge, but the proton's positive, the electron's negative. So 1 proton and 1 electron gives you a charge of 0. 2 protons, 2 electrons gives you a charge of 0. So if you look down there, if you find gold is element, well, it's AU. It's on the 6th row, the 11th column. Sorry, my battleship. AU, how many protons are in gold? 79. So if you have a neutral gold atom, how many electrons? 79. Now there's another number in there as well. The bottom center, which my vision is not clear enough to see. What does it say at the bottom center under the AU? 196.9?
Yeah.
Okay, so that's basically 197. That's the mass, which is just basically adding up the number of protons plus neutrons. So That's basically the number of protons plus neutrons. So you can take the 79, subtract 79 from that number in red, and it tells you how many neutrons. The reason for the decimal is because it's not exact, but it's going to round right. So those elements, we now have some basis for understanding them. They tell us the number of protons. It's arranged with protons increasing as you go from left to right and increasing as you go down. The reason it has the specific columns is because the atoms behave similarly if they're in the same column. So you look up there and you see helium in the right column. Helium is called a noble gas. It doesn't interact with anything. Everything in that right column is likewise a noble gas. It doesn't interact with anything. So you have neon, argon. You can have it around, it's just inert, does nothing. Whereas if you look one column away from that, F for fluorine, fluorine is super highly reactive. It will react with all kinds of things, doing all kinds of nasty stuff. So will chlorine, bromine, iodine, as you go down the column. So that's how it was arranged. The person who gets credit for that table is Mendeleev. I think it's Igor, Ivan, I don't know, Mendeleev. He came up with a chart, something like this, where he was trying to organize them by their chemical properties, putting the more massive ones down lower. The electrons, if you have a metal, metals are really special. With metals, the electrons in the outside are kind of loosely held so that they can travel around. That makes a big difference for electricity. This was a metal because the electrons are kind of loosely held, so I could easily add electrons on here and they'll move all over the place, or I could take electrons off. We call things like that conductors. They conduct electricity because the electrons are free to move and not very strongly bound. Insulators, the electrons are held firmly. You have to put a lot of energy to make them move. You can add electrons to it. You can pull some off, but you can't make them move. So insulators, the electrons can't move around. Conductors, they can. Just another term here, ion. Ion is a term that's used for an atom or a molecule that is not neutral, that has either more electrons or more protons. If it has more protons than electrons, then it has a net positive charge. It's called a positive ion. And we'll usually put a +1 or +2 to say it has one more proton than electron or two more protons than electrons. You can also have a negative ion where you have more electrons. And then we use a -1 or -2, saying it has one less electron one less proton or two less protons. So when we talk about an ion, it's an atom or a molecule that has an electric charge that's not neutral. So once again, with conductors and insulators, you can move electrons about, pull them off very easily with a conductor, not so easily with an insulator. And so I've already talked about these enough. Let's get to our first question. When you brush Fido's fur and scrape electrons from it, so you remove electrons from Fido's fur, what is the charge on Fido's fur after you're done? Fido is, of course, your pet dog.
33?
Yes. All right. I don't know what it's doing. There. Okay, so 5 people said positive, 2 said negative. Mariah, you're the last one that hasn't answered a question yet this semester. So it's your turn to explain your answer. I had a pen. Okay, well, go ahead. What was your answer, and give your reasoning, of course. And why?
Because like I thought that if the electrons were I wasn't exactly sure like what the
Original charge?
charge was.
Okay, so we start with Fido being neutral. Okay, Fido is going to be a box. It's a lot easier for me to draw a box. There's Fido. So Fido initially has a charge of 0. And then we take away electrons. Actually, I should put E minus. The minus tells us the charge is negative. So if we've taken away electrons, what have we left Fido with? Positives, right. So Fido's left with a positive charge because we've removed the negatives. Because one of our fundamental rules in physics, we have lots of fundamental rules, right? We had fundamental rules like energy can't be created or destroyed. Another one is that charge cannot be created or destroyed. We call this a conservation law, so charge is conserved. It can't be created or destroyed. You can take an electron and an anti-electron that can annihilate, but the net charge of electron and anti-electron was 0. So you didn't create or destroy charge, you just remained at 0. So you can't create or destroy charge. So if you remove negative charge from Fido, Fido has to become positive. So there's our term, conservation of charge. This magician here, otherwise known as a physics teacher, is showing you rub fur. His fur is still close to, well, it's not a clump of stuff anymore. It's still on a pelt. And he pulls electrons onto the rod, leaving the fur with what charge? If this is negative, this has got to be positive, so the total charge was conserved. Now, the actual force law for charge is called Coulomb's law, because it was that Charles Coulomb who did all the work, and it has a force equation that looks very much like the equation for gravity that we didn't study hard. For gravity, we learned very carefully force of gravity is mg, but Newton determined that that's equal to the product of two masses divided by their separation squared times a constant. Coulomb determined we have exactly that same form. What does the R mean in my first equation, the one that I wrote? Take a guess. You can be wrong, I'll be happy.
Rate.
Okay, she said rate, not rate. It actually stands for the word radius, but it doesn't mean radius at all. It means the separation between the charges. It comes from the radial distance from one to the other. So that R is the separation. Our textbook uses the letter D rather than R because it's a distance, the distance between the two. If it's gravitational, the two masses. If it's electric force, between the two charges. So the force due to both gravity and electric force is inversely, that's 1 over, proportional to the separation squared. So if you double the separation between two things, you're going to have the force is 1 over 2 squared as big. What's 2 squared? 2 times 2 is 4. So if you double the separation between two charges, you'll have 1/4 of the force.
Wait, can you say that again?
If you double the separation between two charges, you'll have 1/4 of the force. If you triple it, you'd have 1 over 3 squared. What's 1 over 3 squared? 1/9. So if you triple the distance between charges, you'd have 1/9 the force. So the force drops off quickly as they move away. Now in that, there was a constant K, and this is the value for K. Let me just put the units here. So there's the value of K. It's a constant. And I already showed you the charge of an electron is minus 1.6 times 10 to the minus 19 coulombs. Charge of a proton is plus 1.6 times 10 to the minus 19 coulombs. So that's our fundamental unit of charge. Unless you talk about those quarks. The quarks have charges of 1/3 and 2/3 of this. And so any reasonable person would say, well, should the fundamental charge be 1/3 of this? And the physicists say, nay, nay, much like John Finette did before he died. And the reason is quarks are never, ever found alone. They're only found either in quark-antiquark pairs or in triplets like we see back there, or possibly in groups of larger groups. Because they're only found in groups, it turns out that their charges are always going to be multiples of the charge of an electron for the way they group. So that's why our fundamental charge is 1.6 times 10 to the minus 19 coulombs, even though quarks have 1/3 and 2/3 of that. Let's just pass over that. Something that is, once again, going to be important in chemistry is charge polarization. If I have an atom, the atom has what kind of charge in its center? What kind of charge in its center does an atom have? Positive. Has a positive nucleus. And then the electrons, what can I tell you really about the position of the electrons? They're on the outside. It's really all I can tell you. I can tell you the probability of where you're going to find it, but I can't tell you where it is. I can't tell you what its path is doing. It's just moving around. Well, if I bring, let's say, a positive charge close to an atom, what's the positive charge going to do to the electrons that are orbiting the nucleus? Electrons have a negative charge. Bring a positive charge. What's it going to do to that negative charge?
Wait, what did you say?
If I bring a positive charge close to an atom, what's it going to do to the electrons? Attract, because opposites attract. So if I were to bring a positive charge close to the nucleus, or close to an atom, so if I brought a positive charge here, it would be pulling the electrons over toward it and pushing the nucleus away. And in so doing, it separates the symmetry, right? Instead of having a symmetrical situation, I would now have something that's what we call polarized. We've separated that charge a little. And now one side's more positive and one side's more negative. Well, the negative will be closer to the thing that caused it to separate and will be attracted. The positive will be farther away, but if it's farther away, that means it's going to have a weaker force. And so it's going to attract. It's for this reason that water is attracted to both positive and negative. Water is neutral, it has no charge. And we said no charge means that it should just not interact with the electric force. But water molecules are already polarized. Water molecules, most people know water is H2O. So a water molecule is an O bonded to two H's. My broken tip really needs to be replaced. That's why we have all the gaps. I thought I fixed something yesterday and clearly it didn't fix. So that's what a water molecule looks like. Well, the oxygen, it's over there in the 16th column. The oxygen really, really likes electrons. It wants more electrons. And so the oxygen pulls over electrons, and the oxygen has a net charge of like minus 0.70 charge of an electron. The oxygen has 70% of an electron on average. So the electrons from hydrogen have been pulled over by the oxygen atom, leaving the hydrogen atoms with plus 0.35 electron charge on each one. So the water has positive side and negative side. If I bring positive charge near the water, it'll rotate around so the negative is close to the positive. The negative will be closer then than the positive and a stronger force, and it's attractive. If I bring a negative, it'll just rotate the other way, so the positive is closer to the negative. The closer one has a stronger force, and it will be attractive. So water is attracted to either positive or negative charge because of this electric dipole moment, as we call it. That's actually super important because with water, if it's a dipole, you're going to have bonds form because of those dipoles. We call these van der Waals forces. Van der Waals is probably correct. VANDERWAALS. And that makes water so it holds together stronger, which makes water so it will form a ice at a higher temperature. It makes water so it has a much higher heat capacity. These properties make life possible on Earth. If water didn't have this dipole moment and didn't form a van der Waals solid, then you would have problems like the Earth freezing again. So water having these dipoles is actually important to our survival. Which, I mean, you started studying this, and for me, it becomes harder and harder to think that, we just have a randomly designed universe. It seems to me that some wise God, because whether you're a Christian or not, you have to admit, whoever makes the laws for a universe, we're going to consider a God here as humans. Some wise God made these laws so that we could have life form here. Okay, I talked about, that was beautiful. I talked about water. This is something that we've all done, I hope. You take a balloon and you rub it on your head, and you can stick it to the wall and it just stays there. You ever done that? Okay, good. We all had some useful times as children. Why does it stick to the wall? We've talked about all of the things necessary today in class. What's happening when you're rubbing the rubber on your hair?
You're taking away the electrons from your head to the brain.
Okay, it's just like fur, right? My hair is fur. Okay, so is my arms, just for the record. So you're rubbing fur with rubber. That's exactly what I was doing here. What's going to happen? The rubber is going to end up with a negative charge, and the fur is going to end up with a positive charge. So now I have a negatively charged balloon. The balloon's an insulator. The charge isn't free to move. It's pretty much stuck there. I bring it up to the wall, and the wall has electric dipoles in it. Because it has electric dipoles, those dipoles will rotate so that the negative charge on the balloon will make the positives in the wall closer, making the force more attractive than the repulsion, and it sticks to it. It's very cool to do, right? And especially when you got, my grandson's 3 years old. That's the kind of thing that will make him go, ah. And hopefully say Grandpa's really cool. So this picture here is showing you how you induce the dipoles in the wall because of the negative charge on the balloon. New term for you, electric field. This is getting a little harder. Electric field is a thing we use to help us calculate forces easier. The electric field is defined as the force divided by a charge. I'm actually thinking it's a good place to stop here and ask you for 5 minutes any homework questions, because I forgot at the beginning to ask about homework.
Yes. Yes.
Okay, what homework question do you have? I see Mariah, you have one too? Okay. What's your question? Okay, so I guess I should go to the Moodle page and find homework 11. Whoops, that's the wrong account. Login Sesame. Okay. Work faster. You know how some people have no patience? That's me. Okay, number 11. Will Maynez burns a 0.6 gram peanut beneath 50 grams of water, which increases in temperature from 22 degrees to 50 degrees Celsius. The specific heat capacity of water is 1 calorie per gram degree Celsius. And then we have 2 questions. Now what I'm going to do here is copy this problem, paste it in our lecture. Once again, that's good enough. It kind of missed the bottom of it, but I'm going to go to the top of this. So if you're looking for the homework solution, you can just go to today's lecture, and at the top right beside the first slide is the question here. So we have the peanut with mass equals 50 grams, or mass of water is 50 grams. The mass of the peanut is equal to 0.6 grams. Change in temperature is equal to 50 degrees Celsius minus 22 degrees Celsius equals 28 Celsius degrees. Why is it 50 minus 22 and not 22 minus 50? Final minus initial. Excellent. And then we have a number. Specific heat capacity of water is 1.0, and it cut off the end. C is the symbol for that specific heat. 1.0, and what it cut off was calories per gram Celsius degree. And now you're asking, how do I do this problem? The first thing is, if you look in your textbook, in the instructions for this set of problems, it has the equation Q is equal to MC delta T. What does Q stand for in this equation? Heat. So the heat that went into the water is equal to the mass of the water times the specific heat of water times the change in temperature of the water. So we can start off, this isn't our answer, but we can say the heat that went into the water is equal to the mass of the water times specific heat of water times delta T, which is going to be equal to 50 grams times 1 calorie per gram Celsius degree times 28 Celsius degrees equals, 50 times 28, that's half of 28 is 14. Take care of your zeros. So 1,400 calories went into the water. But it didn't have 1,400 calories here. It said, assuming 40% efficiency so that the peanut's food value is 3,500 calories. Well, first I have to take this 40%. So this 1,400 calories is 40% of the energy in the peanut. So if I want to solve for the energy in the peanut, what do I do?
Take out percentage and divide it.
Divide both sides by 40%. Mathematically, how do we write 40%? Okay, so that just becomes 1,400 calories divided by 0.4 equals, and so you pop that in your calculator. 1,400 divided by 0.4. 0.4 is 4 over 10, of course. And so, or 2 over 5. 1,400 times 5 is, I should be able to do this really quickly, right? It's 7. And well, then we have to, I'll just let you do it. You have to divide the 7 by 2, which gives you 3.5. Yeah, trying to make the pen right. Try and be the key here. So 3,500 calories is equal to the energy in the peanut. So that's what it asked us to determine for part B. And then for part C, show the food value in calories per gram. So this is the energy is equal to 3,500 calories. I want it per gram. What was the mass of my peanut? 0.6 grams. So 3,500 divided by 0.6 grams is equal to something that's close to but not equal to 5,800.
5,833.
5 what?
5,833. 0.3.
Oh, yeah, you know. As you can tell from their number, we're going to round here. That rounds to 5,800 calories per gram, or 5.8 kilocalories per gram. A dietary calorie is a kilocalorie, so that's 5.8 dietary calories per gram.
So why is it that in the units above, when you divided it by the 40%, that
Yeah.
you didn't put per gram at the bottom what you did? Like there's no units 0.4. Is it
Right, because that was 40%. There's no units in the percent.
Okay.
Okay, Mariah, what was your question? Number 3? 2? Okay. Yeah, we're over time, so if you have to go, just go. But I am going to help Mariah. Thank you, Sam. Okay, so the one Mariah's looking at, a balloon that weighs 1 Newton is suspended in air during drifting neither up nor down, so it's staying at constant elevation in equilibrium, neutrally buoyant. How much buoyant force acts upon it? Neutrally buoyant, right? If it stays at the same height, what's its acceleration? No, if it stays at the same height, then its velocity is constant at 0. And since acceleration is the change in velocity divided by change in time, if the velocity is remaining constant, the acceleration is 0. So the acceleration is 0. Therefore, sum of the forces equals 0, because sum of the forces is mass times acceleration. And so that means that if I look at my balloon, here's my balloon. It's going to have the force of gravity downward, 1 Newton. And it's going to have the force buoyant upward. But if those add to 0, how big is the force buoyant going to have to be? Not 0. If it was 0, I would notice I have force buoyant minus the force of gravity, so minus 1 Newton equals 0. If the force buoyant was 0, I'd have 0 minus 1 is equal to 0. What's the force buoyant going to have to be? So if I subtract 1, it gives me 0. It's got to be 1. It's got to be 1 Newton so that the net force, when I add them all up, comes to 0. And then what happens if the buoyant force decreases or increases? So if the weight stays the same and the buoyant force goes up, then I'm gonna have more force in which direction, up or down? Pulling force goes up, I'll have more up, because it's the one that's pointing up. So then my net force would be up.